Welcome to Talk Tensors. It is incredibly great to have you with us today. We are doing a deep dive into the source material that basically, well, it permanently altered the trajectory of deep learning on graph-structured data.
Yeah, it really set the standard.
Right. We are talking about the seminal paper from that 2016-2017 era, Semi-Supervised Classification with Graph Convolutional Networks. And, you know, if you're prepping for a high-level architecture meeting or trying to build a fundamental understanding of modern machine learning topology.
Or honestly, if you're just insanely curious about how we mathematically model the interconnectedness of literally everything.
Exactly. From sprawling citation networks to the underlying structures of the internet itself, you were in exactly the right place.
It truly is a brilliant piece of work. Just to give you the one-sentence thesis right up front, this paper successfully bridged the gap between neural networks and graph theory by introducing a simple, highly scalable first-order approximation of spectral graph convolutions.
Which is a mouthful, I know.
It is, but it basically took a process that was computationally agonizing, mathematically dense, and practically impossible to scale, and distilled it into this elegant, efficient architecture. It forms the bedrock of what we now take for granted in graph representation learning.
And to make sure we unpack the actual mechanics of how they pulled that off, here is how we are structuring our deep dive today. We're going to start by painting a picture of the historical landscape, what the field looked like before this architecture existed, and the massive computational roadblocks researchers were slamming into.
Right, the pre-GCN era.
Yeah. And from there, we are going to dive straight into the math, translating things like spectral convolutions in the Fourier domain and Chebyshev polynomials into tangible, workable concepts. We'll even walk through a literal mathematical simulation of a tiny graph so you can see the exploding gradient problem and the paper's brilliant renormalization trick fix.
Following that, we will examine the actual experimental benchmarks to see how this model performed in extreme low data environments, including a massive knowledge graph.
Which is mind-blowing.
It really is. We'll also tackle a fascinating theoretical quirk known as the depth paradox. Why making this specific type of network deeper actually destroys its performance, which directly contradicts modern deep learning intuition.
Totally backwards from ResNets.
Yeah.
And then we'll explore a beautiful mathematical symmetry with a classic 1960s isomorphism algorithm, apply it to the famous Zachary's Karate Club sociology dataset, and finally, outline the model's limitations.
And, of course, we will wrap up with our novel notions brainstorming segment where we pitch some highly experimental, completely unverified future research ideas inspired by the paper's legacy.
So let's jump right into the landscape of the time. What was the exact problem this paper was trying to solve? Because the entire framing hinges on this concept of semi-supervised node classification and specifically transductive learning.
Yeah, the transductive setting is absolutely crucial to understand here. In standard inductive supervised learning, say image classification, you train a model on a massive data set of labeled cat and dog photos. Once it is trained, you deploy it and you hand it a brand new unseen photo of a cat and it predicts the label. The model generalizes to unseen data. Transductive learning on a graph is a completely different beast.
Because in transductive learning, you already have the entire universe of data, the whole graph sitting right in front of you during the training phase. You aren't expecting new nodes to magically appear later.
Correct. You have the entire graph structure, you can see all the nodes, and you can see exactly how they are connected via edges. But here's the catch. You only have labels for a microscopic fraction of those nodes.
Like an academic citation network.
Exactly. Imagine a massive network with millions of published papers. You know exactly which paper cites which other paper. You even have the text features, the abstract, or the keywords for every single paper.
But you only know the actual category label like quantum physics or organic chemistry for maybe 20 papers out of a million.
Yes, your objective is to accurately propagate those few known labels across the millions of unlabeled nodes using the geometry of the network.
Which sounds straightforward until you try to actually program a neural network to do it. Before this paper came along, researchers were trying a few different avenues, and they were all basically hitting brick walls.
Let's look at graph Laplacian regularization, things like label propagation or manifold regularization. The foundational assumption there was basically guilt by association, right?
That is a highly accurate way to phrase it. The underlying mathematical assumption of graph Laplacian regularization is homophily. It assumes that connected nodes are inherently similar and therefore should share the same label.
So they just smoothed it out.
Pretty much. Researchers would bake a regularization term into their loss function that heavily penalized the model if two connected nodes were assigned different labels. They were essentially forcing the network to mathematically smooth the label information over the graph's topography. Let me stop you right there, because treating every connection as a proxy for similarity seems like a massive oversimplification. I mean, if I am writing a machine learning paper and I cite a biology paper because I'm applying an algorithm to a biological data set, my paper doesn't suddenly become a biology paper.
That is the exact flaw the authors of this paper highlighted. Edges in a complex graph do not merely encode similarity. They contain rich, asymmetrical, highly contextual information.
Right.
An edge might represent a dependency, a historical contradiction, a predator-prey relationship in a food web, or a sequential progression. If your mathematical model fundamentally assumes that an edge just means these two things are identical, you severely restrict the modeling capacity of your neural network. You are forcing a blunt smoothing operation over a highly nuanced topology.
So the smoothing approach was too blunt. But there was another massive trend dominating the landscape at the time, which was graph embedding methods. I'm talking about DeepWalk and Node2Vec. Now, to truly appreciate why the Graph Convolutional Network was such a breakthrough, we need to spend some time unpacking how DeepWalk actually worked, because it was heavily inspired by the natural language processing world. Specifically, the word-to-vec skipgram model.
The intersection of natural language processing and graph theory during that era was fascinating. In NLP, Tomas Mikolov's word-to-vec revolutionized the field by demonstrating that you could learn dense vector representations, embeddings of words based on their context.
Context is everything.
Exactly. The skipgram architecture looks at a target word in a sentence and tries to predict the surrounding context words. The core philosophy is that words appearing in similar contexts share similar semantic meanings.
So the DeepWalk researchers looked at that and thought, well, how can we turn a massive unstructured graph into a series of sentences so we can just use the NLP skipgram model?
Precisely. And their solution was the random walk. Imagine dropping a digital walker onto a random node in your citation graph. The walker randomly picks an edge, walks to the connected node, picks another random edge, walks to the next node, and repeats this for, say, 40 steps.
And that sequence of 40 visited nodes is now treated exactly like a sentence of 40 words.
It is.
That is actually an incredibly clever workaround. You generate thousands and thousands of these random walks, feed them into the skipgram architecture, and the model learns node embeddings based on which nodes frequently appear in the same sentences or random walk sequences.
It is clever, and it produced state-of-the-art results at the time, but it possessed a fatal flaw when it came to efficiency, scaling, and end-to-end optimization. Think about the pipeline required to actually classify nodes using this method. It is incredibly disjointed. Well, first, you have to compute and store millions of random walks. Second, you have to train the unsupervised skipgram model to generate the node embeddings. Third, you have to freeze those embeddings, take them out, and plug them into a completely separate semi-supervised classifier-like, a logistic regression model to actually predict the labels.
So it's a multi-step segmented pipeline, which means it's not end-to-end differentiable. The final classifier that is trying to predict quantum physics cannot send error signals gradients all the way back to the random walk generation phase.
Exactly.
It can't tell the walker, hey, your random walks are ignoring a crucial community structure. Please adjust your walking parameters. The graph structure extraction and the classification are completely severed from each other.
That lack of end-to-end differentiability was a massive bottleneck. The system cannot learn from its own mistakes globally. This is the precise historical moment where the graph convolutional network enters the picture. Kipf and Welling didn't invent the concept of a graph convolution out of thin air. They built upon an incredibly rich intellectual lineage, specifically the foundational, highly complex spectral graph convolutional networks developed by Joan Bruna and later extended by Michael DeFerrard.
But those earlier models were notoriously difficult to implement at scale, which brings us to the core methodology and the genius approximation of this paper. To appreciate what Kipf and Welling did, we have to look at how convolutional neural networks, or CNNs, operate on images, and why that standard spatial approach completely falls apart when you hand it a graph.
In traditional computer vision, a spatial convolution is straightforward. An image is a perfect, rigid grid of pixels. If you want to convolve a specific pixel, you define a fixed 3x3 filter, drop it over the pixel, and you know with absolute mathematical certainty that you will be multiplying the central pixel and exactly 8 adjacent neighbors. The receptive field is uniform.
Right, but a graph has no uniform grid. A graph is completely unstructured. If I look at a user node on a social network, they might follow one person. The next user node might follow 10,000 people. If you try to slide a fixed 3x3 spatial filter across that, the math instantly breaks. You cannot define a uniform spatial neighborhood.
Because you cannot rely on spatial uniformity, the earlier pioneers like Brunner realized they had to abandon the spatial domain entirely and move into the spectral domain. They turned to spectral graph theory. Instead of trying to convolve the features across the physical connections, they transformed the entire graph and its features into the Fourier domain.
Okay, let me make sure I'm tracking this, because this is where the math gets incredibly dense. In signal processing, moving to the Fourier domain means decomposing a signal into its constituent frequencies. But how do you find the frequencies of a citation network?
You utilize the graph Laplacian. If you take the degree matrix, which just lists how many connections each node has, and you subtract the adjacency matrix, which maps exactly who is connected to whom, you get the graph Laplacian.
Okay, degree minus adjacency.
Yes. This matrix essentially captures the structural dynamics of the entire network. To do a spectral convolution, you have to compute the eigendecomposition of this normalized graph Laplacian. You extract its eigenvectors, which act as the Fourier basis, the frequencies of the graph. You then multiply your node features by a filter parameterized by these eigenvectors.
And right there is the computational nightmare. Computing the eigendecomposition of a matrix is incredibly expensive. If you have a graph with n nodes, doing this the old way has a big O of n squared complexity. If your graph has 100,000 nodes, you're suddenly looking at billions of operations. For 1,000,000 nodes, it is 1,000,000,000,000 operations just for the matrix multiplication, not to mention the astronomical cost of finding the eigenvectors in the first place.
It's massive.
It is a brilliant theoretical concept that is practically useless for internet-scale datasets. It simply scales terribly.
It was a huge mathematical bottleneck. To circumvent this, earlier researchers, specifically Hammond and Deferard, introduced a highly technical shortcut. They realized you didn't actually need the full, exact eigendecomposition to get a useful filter. Instead, you could approximate the spectral filter using a truncated expansion of Chebyshev polynomials.
Chebyshev polynomials are fascinating. They are a sequence of orthogonal polynomials that are incredibly efficient at approximating other complex functions. So instead of calculating the exact frequencies of the entire massive graph, you approximate them by expanding these polynomials up to a certain chosen order, which the literature refers to as order k.
Exactly. And the order k is the critical variable here. When you use a Chebyshev polynomial approximation up to order k, it has a very specific physical manifestation on the graph. It turns a global spectral operation into a strictly k-localized spatial convolution.
So it bounds it.
Yes. If you expand the polynomial to k equals 3, the convolution operation at any given target node will only aggregate feature information from nodes that are, at maximum, 3 hops away. It restricts the receptive field to the kth order neighborhood.
And the computational savings there are monumental. Suddenly, you aren't multiplying dense matrices of the entire graph. You are only looking locally. The complexity drops from that disastrous big O of n squared down to big O of the absolute value of e, meaning the computational cost scales linearly with the number of edges in the graph.
Which is what makes it actually feasible.
Right. But here is the stroke of absolute genius in the Kipf and Welling paper. They looked at this highly complex, multi-hop Chebyshev approximation, and they made a radical decision.
They decided to set k equal to 1. They took this incredibly powerful polynomial expansion designed to reach deep into a graph structure, and they forcefully truncated it at exactly 1 hop. Instead of using higher-order polynomials to look 3 or 4 steps away, they limited the layer-wise convolution to look strictly at a node's immediate direct neighbors.
Wait, if we do that, aren't we just throwing away all the global structural information? How does the neural network see the broader graph if every single layer is entirely blind to anything past its next-door neighbor?
That is the beauty of deep learning. You recover the larger receptive field through depth. By limiting the layer-wise operation to k equals 1, the complex Chebyshev polynomial collapses into a remarkably simple linear function on the graph Laplacian spectrum. It becomes an incredibly lightweight, fast operation. And to see further into the graph, you simply stack multiple layers of this lightweight operation, inserting nonlinear activation functions like ReLUs between them.
I see. So in layer 1, node A aggregates information from its direct neighbor, node B. But in layer 2, node A aggregates information from node B again, except this time node B's features have already been updated by its neighbors from layer 1.
You've got it.
So by stacking 3 simple k equals 1 layers, node A effectively absorbs information from 3 hops away, but with nonlinear feature transformations happening at every single step.
Precisely. You effectively convolve the kth order neighborhood by stacking k independent layers. This is vastly superior to explicitly parameterizing a single complex Chebyshev filter for several reasons. First, the explicit Chebyshev polynomials have a massive number of parameters.
That sounds like an overfitting risk.
Oh, massive overfitting. In highly connected data sets, like a social network where some central nodes have tens of thousands of connections, those high-order filters will aggressively overfit to the local neighborhood structures. By collapsing it to a linear formulation, you inherently regularize the model. Second, for a fixed computational budget, this lightweight operation allows you to build a deeper, more expressive neural network.
It's a profound simplification. They took dense spectral graph theory and distilled it into a clean, differentiable operation. But translating that elegant theory into stable Python code introduces a completely new set of headaches. If you just naively multiply these aggregated matrices, the whole network blows up. Let's look at the actual architecture and let's walk through a simulated mathematical pass of a tiny graph so you can literally visualize what is happening inside the matrices.
Okay, let us construct a microscopic network. Imagine we have exactly 3 nodes, node 1, node 2, and node 3. Node 1 is our central sub. It is connected to both node 2 and node 3. However, node 2 and node 3 are only connected to node 1. They are not connected to each other.
Okay, simple enough. Now we need our inputs. The first input is X, the feature matrix. Let's say these nodes are academic papers. X contains the bag of words representation of their abstracts.
Right.
The second input is A, the adjacency matrix. This is a 3x3 grid of ones and zeros that maps our connections. So row 1 of matrix A would have a 1 in the second column and a 1 in the third column, representing its links to node 2 and 3.
Now, the most basic way to aggregate information from your neighbors is to simply multiply the adjacency matrix A by the feature matrix X. When you compute A times X, the matrix multiplication automatically sums up the feature vectors of all adjacent nodes.
So for node 1,
it takes the feature vector of node 2, adds it to the feature vector of node 3, and that becomes node 1's new representation.
But there is a glaring massive problem with that. Node 1 just aggregated the features of its friends, but it completely erased its own features in the process.
Yes, it did.
Because the diagonal of the adjacency matrix A is full of zeros, nodes aren't typically defined as being connected to themselves. Node 1's original abstract is entirely lost. If you are trying to classify a paper, you cannot ignore the paper's own content.
Exactly. To rectify this, Kipf and Welling introduce A tilde. A tilde is simply the original adjacency matrix A plus the identity matrix, denoted as I sub n. The identity matrix is a matrix with one straight down the diagonal. By adding it, you are mathematically forcing a self-loop onto every single node. Now, when you multiply A tilde by X, node 1 sums up the features of node 2, node 3, and itself.
Okay, so we preserve the node's own data, but we immediately run into a second, arguably more dangerous problem, scale. In our tiny graph, node 1 is summing up 3 total feature vectors. Node 2, which only has 1 connection, is only summing up 2 vectors itself in node 1.
So disparity.
Yeah. In a real-world citation network, a highly cited paper might sum up features from 10,000 neighbors, resulting in massive numerical values, while an obscure paper only sums up 2 values. The scale of the feature vectors will be completely distorted across the graph.
And this distortion will completely derail the learning process. To stabilize the scale, we must introduce the degree matrix, specifically D tilde. The degree matrix is a diagonal matrix that simply counts the total number of connections each node has in A tilde. To normalize our aggregation, we need to divide by these connection counts.
Makes sense.
The traditional way to do this in graph theory is to multiply by the inverse of the degree matrix, calculating D tilde inverse times A tilde. This mathematically changes the aggregation from a sum of neighboring features to an average of neighboring features.
Which sounds perfectly reasonable. But if we do that, if we just use a simple average normalization and stack multiple layers of this in a deep neural network, we step right onto a hidden mathematical landmine.
The exploding gradient problem.
Yes.
If you analyze the spectrum of the standard D tilde inverse times A tilde operator, you will find that its eigenvalues lie within the range of 0 to 2. In the context of a deep neural network, you are repeatedly multiplying the input by this operator layer after layer during the forward pass, and repeatedly multiplying by it again during the backpropagation of error gradients.
So it's acting like a compounding interest rate. If you repeatedly multiply a value by numbers that can be up to 2 across 10 or 20 layers, those numbers grow exponentially. The gradients explode to infinity, or they vanish entirely to zero. The network essentially hyperventilates and mathematically collapses. It cannot learn.
To defuse this landmine, the authors introduced what they call the renormalization trick. Instead of the traditional asymmetric average normalization, they utilize symmetric normalization. The exact formula is d tilde to the -1/2 times a tilde times d tilde to the -1/2.
So they are multiplying the augmented adjacency matrix by the inverse square root of the degree matrix on both sides. What does that actually do to the data flow?
It acts as an immaculate pressure valve. By applying the inverse square root symmetrically, it squashes the eigenvalues of the operator, bounding them strictly within the range of -1 to 1. It prevents the exponential explosion of values.
That's elegant.
It is. More intuitively, it scales the message passing based on the connectivity of both the sender and the receiver. If node A is sending features to node B, the signal is dampened if node A has thousands of connections, meaning its individual signal is less unique, and it is also dampened if node B receives thousands of connections, preventing node B from being overwhelmed.
It perfectly balances the flow of information across the entire network, regardless of how skewed the degree distribution is. When you implement this renormalization trick, you get a single, ultra-stable, highly efficient forward pass that seamlessly merges local graph topology with high-dimensional node features.
It's a stunning piece of mathematical engineering.
And because it relies on sparse matrix multiplication, it maintains that crucial big O of the absolute value of E linear scaling. You can run this on massive datasets on a single GPU.
But theory and mathematical elegance are paramount. They mean nothing if the architecture fails to perform empirically. This brings us to the actual experiments. The experimental design Kipf and Welling utilized was rigorous, focusing heavily on transductive, extreme, low-data environments.
Let's look at the datasets they used to benchmark this model. They tested on 3 standard academic citation networks: Cora, CiteSeer, and PubMed. In these datasets, the nodes are the published documents, the edges are the citation links, and the features are sparse bag of words vectors.
Yeah.
For those unfamiliar, a bag of words simply takes the entire vocabulary of the dataset, assigns a specific index to every possible word, and represents a document as a giant array of mostly zeros, with ones indicating which specific words appeared in that document's abstract.
The citation networks are standard benchmarks, but the authors also tested the GCN on a substantially more complex and challenging dataset called NEL, which stands for Never-Ending Language Learning.
I love NEL.
It's wild. NELL is an immense knowledge graph extracted from reading millions of web pages. It is not a simple network of documents citing documents. It consists of entities like Microsoft or Seattle and relations like headquartered in.
And a standard GCN cannot natively process relations. It only understands nodes and edges. So how did they feed a knowledge graph into this architecture?
They executed a bipartite graph extraction. They transformed the distinct relations into standard nodes themselves. So instead of an edge labeled headquartered in connecting Microsoft and Seattle, you have a node for Microsoft connected to a newly created node representing the headquartered in relation.
Which is then connected to the node for Seattle.
Exactly. This creates a massive bipartite structure with over 65,000 nodes and 266,000 edges. It dramatically increases the complexity of the classification task.
And we have to emphasize the sheer lack of labeled data the model was given to solve this task. This was not a supervised image classification task where the model trains on 1 million labeled examples. This was an exercise in extreme semi-supervised learning. For the Cora, CiteSeer, and PubMed networks, they restricted the training data to a mere 20 labeled examples per class. They hid the labels for the remaining thousands of documents. But the NEL setup was borderline absurd.
For the massive NEL knowledge graph, the model was restricted to exactly 1 single labeled example per class in the training set.
1 label.
It is almost mathematically unfathomable to task a neural network with accurately classifying tens of thousands of complex entities across 210 distinct categories when you only permit it to observe 1 solitary example of what each category represents.
It is a phenomenal stress test of the architecture's ability to extrapolate using pure geometry. So what happened when they finally hit run?
The Graph Convolutional Network achieved a significant margin over all existing baselines, which is notoriously difficult to accomplish in transductive settings. On the widely benchmarked Cora dataset, the GCN achieved an 81.5% classification accuracy.
Wow.
To put that in perspective, the closest competitor at the time, a model called Planetoid, plateaued at 75.7%. The GCN generated a massive leap in predictive power.
But the accuracy isn't even the most impressive metric here. The efficiency of the model absolutely validated all that dense mathematical theory we just discussed. Because they reduced the spectral convolution to a localized k=1 linear operation, the model trained incredibly fast. On the Cora dataset, the GCN converged to its maximum accuracy in just 4 seconds of wall clock time.
4 seconds.
Planetoid, the runner-up in accuracy, took 13 seconds. The GCN was not only significantly more accurate, but it was also operating at more than 3 times the speed. On the massive NEL knowledge graph, the GCN finished training in 48 seconds, while Planetoid required over 3 minutes.
The authors also conducted a comprehensive ablation study to prove that their specific mathematical choices were the precise drivers of this performance. They systematically tested variants of their own model. They stripped out the renormalization trick and tested a naive first-order model. They also tested the more complex, computationally heavy, higher-order Chebyshev filters, specifically setting k=2 and k=3.
And the data perfectly vindicated their theory. The variant utilizing their symmetric renormalization trick outperformed everything else. It handily beat the naive first-order models, definitively proving that the symmetric normalization was acting as that critical pressure valve for numerical stability. And, most importantly, it beat the higher-order Chebyshev filters. It proved that their core intuition was flawless. Setting the localized filter to k=1 and stacking multiple layers was vastly superior to explicitly parameterizing larger neighborhood filters.
Because explicitly parameterizing a larger spatial filter on an unstructured graph almost guarantees that you will overfit the local topology of high-degree nodes. Stacking linear localized layers provides the necessary regularization.
But let me challenge that exact conclusion. We just established that stacking multiple layers of a simple k=1 filter is better than running a single complex layer. But that brings us face to face with incredibly interesting contradiction in the paper.
The depth paradox.
Yes. In modern deep learning, especially if you look at architectures like ResNets in computer vision or massive transformers in NLP, the golden, unbreakable rule is that deeper is always better. If a 10-layer network is good, a 100-layer network is extraordinary. It allows the model to learn exponentially more complex, hierarchical feature representations. So what happens when you take a GCN and make it 10 layers deep?
Kipf and Welling ran a cross-validation experiment to test this exact hypothesis. They scaled their graph convolutional network from a single layer all the way up to 10 layers. The empirical findings were entirely counterintuitive to traditional deep learning dogma.
It broke, didn't it?
It did. The optimal classification results were consistently achieved with highly shallow networks, specifically architectures with just 2 or 3 layers. As they added more layers beyond that, the accuracy did not simply plateau, it actively and aggressively degraded. A 10-layer GCN performs significantly worse than a basic 2-layer GCN.
Why does a graph convolution network suddenly tear itself apart when it gets too deep? Why does the fundamental rule of deep learning fail here?
The diagnosis highlights a fundamental topological difference between image grids and graph networks. With every single layer you add to a GCN, a node's effective receptive field, its context size grows by an entire degree of neighborhood connectivity. In layer 1, a node aggregates features from its immediate friends. In layer 2, it aggregates features from the friends of its friends.
Right.
In a highly connected graph, the number of nodes included in this receptive field expands exponentially with every hop. By layer 7 or 8, a single central node is essentially pulling in aggregated feature data from almost the entire interconnected graph.
Ah, I see the problem. It is an extreme case of oversmoothing. If node A is pulling in data from the entire network, and node B is also pulling in data from the entire network, their resulting feature vectors are going to look virtually identical. The unique, localized, discriminatory features of an individual node get completely washed out by the global mathematical average.
Exactly. The representations lose all variance. Furthermore, increasing the depth vastly inflates the number of trainable weight parameters in the model. When you combine a massive parameter count with a receptive field that spans the entire dataset, it leads directly to catastrophic overfitting on the training labels. The model completely loses its ability to generalize.
Now, the authors were aware of this, and they tried to borrow a well-known trick from computer vision to fix it. They implemented residual connections, the exact same skip connections utilized in ResNet.
Oh, right, adding the input forward.
Yeah, the mathematical theory is that by adding the original unsmoothed input of a previous layer directly to the output of the current layer, you can carry the sharp, localized node features deeper into the network, counteracting the over-smoothing effect. Did that solve the depth paradox?
It was a mathematically sound attempt, and the residual connections did provide some structural stability. They prevented the accuracy of the deeper models from cratering quite as drastically as the standard models. However, it ultimately failed to cure the underlying pathology.
So it was just a Band-Aid.
Pretty much. Even heavily stabilized with residual connections, a 10-layer GCN simply could not match the sheer accuracy and efficient generalization of a straightforward 2- or 3-layer architecture. For this specific class of spectral graph convolutions, shallow and wide is definitively superior to deep and narrow.
That is such a fascinating counterintuitive quirk of modeling graph data. Now, we are moving into what is honestly my absolute favorite part of this entire deep dive. The paper reveals a truly beautiful piece of theoretical symmetry between their cutting-edge neural network and a classic 1960s algorithmic concept.
To fully appreciate the elegance of this connection, we first need to define the one-dimensional Weisfeiler-Lehman algorithm, universally referred to as WL1. Developed in 1968, it is a foundational algorithm used in computer science for testing graph isomorphism.
And graph isomorphism is the problem of determining if two graphs, which might be drawn completely differently on a piece of paper, actually possess the exact same underlying structural connectivity.
Correct. The way WL1 tests for this is fascinating. It iteratively hashes the labels or the colors of a node and its neighbors. Let's say we have a tiny graph with colored nodes. I have a red node. I am connected to a blue node and a green node.
Okay, red, blue, green.
The WL1 algorithm takes my color, red, and my neighbor's colors, blue and green, and passes them through a strict hashing function. It generates a brand new, unique signature, let's call it purple, and assigns that as my new color. And it executes this hashing process simultaneously for every single node in the graph, over and over again, until the coloring scheme of the entire graph stabilizes and stops changing.
So it cascades through the network.
Yes. If two graphs stabilize into the exact same color distribution, they are highly likely to be isomorphic.
It is a discrete, rigid, highly effective structural test. And what Kipf and Welling proved in this paper is that their GCN propagation rule, the very formula we spent the first half of this deep dive building, is essentially a continuous, fully differentiable neural network generalization of the WL1 algorithm.
That is incredible. The GCN is doing the exact same thing, but with continuous math instead of discrete hashes.
Exactly. Instead of using a rigid, discrete hash function, the GCN utilizes a continuous learnable weight matrix and a differentiable nonlinear activation function. Instead of categorical colors, it passes high-dimensional continuous feature vectors. But structurally, architecturally, it is executing the precise same iterative neighborhood aggregation and structural signature creation as the 1968 algorithm.
Which means that, by its very mathematical nature, the GCN architecture is inherently predisposed to understand and extract complex graph topologies. And the authors demonstrated this inherent capability using one of the most famous datasets in all of network science, Zachary's Karate Club.
Let me give you the quick historical context on this dataset because it adds so much color to the math. In the 1970s, a sociologist named Wayne Zachary embedded himself in a university karate club for 3 years. He tracked the social interactions of the 34 members outside of the club, mapping out 154 edges of friendship.
And then drama struck.
Massive drama. A massive political and financial dispute broke out between the club's instructor and the club's president over the pricing of karate lessons. The tension escalated until the club literally fractured and split into two rival factions.
Because of that documented sociological fracture, it is the perfect real-world baseline dataset for testing community detection algorithms. It perfectly maps structural connectivity to a known sociological outcome. And here is the truly staggering finding detailed in the paper. The authors constructed a 3-layer GCN, but they did not train it.
Wait, they didn't train it?
Nope. They initialized the network with completely random weight matrices. They did not feed it any node labels. They did not run a single step of gradient descent or backpropagation. They simply took the raw Karate Club graph structure and passed it forward through the randomized matrix multiplication.
And what was the result of passing data through random math?
Because the GCN architecture is effectively a continuous Weisfeiler-Lehman algorithm, the structure of the network itself acts as an incredibly potent feature extractor. Even with completely random, untrained weights, the model naturally embedded the 34 nodes into a two-dimensional space where the two rival karate club factions, the instructor's loyalists and the president's loyalists, were cleanly separated from each other.
That is nuts. An untrained neural network, using literally random parameters, naturally mirrored the complex sociological modularity of human relationships, rivaling the embeddings produced by the heavily trained, highly optimized DeepWalk model. The physical structure of the equation is doing the heavy lifting, not just the trained parameters.
It is a stunning visual validation of their mathematical theory. And furthermore, when they finally did apply a microscopic amount of training, providing the model with just 4 labeled nodes, essentially 1 anchor for each community subclass, the model successfully separated the entire club perfectly with linear boundaries in the embedding space over just 300 iterations.
So it mathematically learned the nuanced sociology of the club almost instantaneously, based purely on the structural geometry of the graph.
It is an absolute triumph of architectural design.
It really is. But of course, no model is a panacea, and one of the hallmarks of a truly foundational paper is the author's rigorous self-awareness. Kipf and Welling actively outline several severe limitations and theoretical blind spots in their conclusion. Let's examine those limitations, starting with the physical hardware constraints. Because they utilize full batch gradient descent, there is a massive memory bottleneck, isn't there?
Yes, the memory constraints are significant. In their experimental setup, the entire feature matrix, the entire data set of labels, and the fully augmented adjacency matrix must be loaded into the GPU's active memory simultaneously. Because the algorithm's complexity is big O of the absolute value of E, the memory requirement scales linearly with the number of edges.
Which is fine for small networks.
Right. While that is perfectly acceptable for academic citation networks with a few 100,000 edges, if you attempt to deploy this on a commercial scale, say, analyzing the global Facebook social graph with billions of edges, it will instantly trigger an out-of-memory error on any existing hardware.
And moving to a standard mini-batch training setup where you only load a small fraction of the data at a time, like we do in image processing, is uniquely problematic for graph networks. If you sample a mini batch of 10 nodes to calculate their forward pass, you have to load all of their neighbors into memory. And if you have a 3-layer network, you have to load their neighbors' neighbors and their neighbors' neighbors' neighbors.
Yes, because of the density of modern graphs, sampling just 10 target nodes might require you to load 50% of the entire graph into memory anyway. It is known as the neighborhood explosion problem.
Neighborhood explosion.
Exactly. Mini-batching requires complex subgraph sampling techniques that were beyond the scope of this specific foundational paper. Another significant limitation is the model's handling of edge types. The mathematical derivations they provided fundamentally assume an undirected, unweighted graph.
Right. It lacks native support for directed edges, where a structural relationship only flows in one direction, like a Twitter follow or edge features, where the link itself contains quantitative data, like the duration of a phone call between 2 users. Now, they bypass this limitation on the NELL dataset by using that bipartite graph extraction workaround we discussed earlier, turning relations into temporary nodes. But that is a manual preprocessing workaround. It is not a native learned feature of the architecture.
Finally, the authors astutely pointed out a rigid mathematical assumption hidden within their own renormalization trick. When they constructed the A tilde matrix, but simply adding the identity matrix I sub n to the adjacency matrix A, they implicitly hard-coded a fixed equal weighting between a node's internal self-connections and its external neighboring edges.
The model mathematically assumes that your own personal features are of exactly equal importance to the aggregated sum of all your friends' features.
Correct. And that might not be true for every dataset. The authors theorized that in future research, one could introduce a learnable trade-off parameter, a lambda value, into the adjacency matrix. This would allow the neural network, via gradient descent, to dynamically decide whether to prioritize a node's internal features or the structural signals from its surrounding neighborhood, adjusting that balance layer by layer.
They essentially published a roadmap for the next decade of graph neural network research right there in the conclusion. And speaking of the future of research, that brings us to the final and certainly the most speculative segment of our deep dive. It is time for novel notions.
I must preface this, as always, with a strict disclaimer. This segment is entirely for entertainment and theoretical exploration. We are extrapolating the core methodology of the paper into extreme, unverified, and highly speculative domains. These are thought experiments, not peer-reviewed scientific claims.
Absolutely. We take the brilliant mechanics Kipf and Welling built and push them to their absolute, logical, or perhaps somewhat illogical extremes. Pitch me idea number 1.
I call this concept parameterized dynamic adjacency, or the living graph. In the architecture we just spent the hour dissecting, the adjacency matrix A tilde is a rigid, static construct. It is calculated during a data pre-processing step, loaded into the GPU memory, and it never changes. The network learns complex weight matrices to interpret the data flowing over the graph, but it cannot alter the physical structure of the graph itself. But directly inspired by their own acknowledged limitation regarding edge weighting, what if the topology was not static?
Okay, I am intrigued. How would a dynamic topology function?
What if we initialize the training process with the standard adjacency matrix A tilde, but we recast the binary edge connections, the ones and zeros, as continuous, differentiable, trainable parameters? As the neural network calculates its classification loss and backpropagates the error gradients, we allow those gradients to continuously rewrite the graph's actual connective tissue in real time.
That is fascinating. So as the neural network is struggling to classify the nodes, it might analyze a specific edge connecting a machine learning paper to a biology paper and decide, you know what, the information flowing across this specific link is actively increasing my classification error. I am going to dynamically reduce the weight of this edge to 0. It is essentially performing unsupervised, self-directed graph pruning while simultaneously classifying the nodes.
Exactly. The graph topology transforms into a living, trainable parameter. The primary experiment to validate this would be captivating. We would construct a highly noisy citation network. We would take a clean data set and intentionally inject tens of thousands of fake randomized citation links, creating a chaotic, densely connected hairball. We deploy the living graph model and monitor the adjacency matrix during training.
To see if it fixes itself.
Precisely. If the hypothesis holds, we would mathematically observe the network's backpropagation naturally and aggressively severing those injected noisy edges to intentionally isolate subcommunities, minimizing its classification loss. The physical structure of the graph would organically shift, break apart, and crystallize into tighter, cleaner clusters as the training epochs progress.
The model would physically reconstruct the reality of its own environment to make its job easier.
That is an incredible concept. Okay, I have idea number 2, and it directly tackles the depth paradox we diagnosed earlier. We know that the 10-layer GCN failed catastrophically because the localized neighborhood context expanded too rapidly, pulling in the entire graph and mathematically washing out all the unique node features. I call my theoretical solution infinite depth GCNs via temporal decay.
How exactly do you intend to circumvent the over-smoothing problem without relying on residual skip connections? By modifying the renormalization trick to include a geometric decay parameter that is strictly tied to the depth index of the layer. In the current Kipf and Welling formulation, every single layer propagates information with the exact same raw mathematical intensity. The layer 10 aggregation is just as aggressive as the layer 1 aggregation. But what if we forcefully penalize the influence of the neighborhood aggregation the deeper we travel into the network architecture?
Walk me through the mechanics of that penalty.
We construct an extreme architecture, let's say a 50-layer graph convolutional network. But we modify the propagation rule so that the aggregation influence of any given layer L is penalized by a geometric factor of 1/2 to the power of L.
Ah, I see the mathematical intuition. In layer 1, a node absorbs 50% of the feature information from its immediate neighbors. In layer 2, when it aggregates again, it only absorbs 25% of the information. By the time the data reaches layer 10, the node is only absorbing a microscopic fraction of a percent of the broader global graph's mathematical noise.
Precisely. It allows the neural network to maintain deep, highly complex, multi-layered weight parameters to execute intricate feature transformations, giving us the representational power of a ResNet without suffering the catastrophic washing out effect of the entire graph structure collapsing the embeddings. It perfectly mathematically simulates the way physical ripples in a pond naturally decay and lose energy over distance. You could theoretically deploy a 100-layer GCN that leverages massive deep learning capacity while still retaining perfectly sharp, highly localized node features.
That is a highly plausible, mechanically sound architectural modification. By mathematically capping the asymptotic limit of the neighborhood aggregation, you could potentially unlock the true, scalable power of deep residual learning for complex graph structures, bypassing the depth paradox entirely.
But we will leave the coding and validation of the living graph and temporal decay models to the brilliant PhD students tuning in. But before we sign off, I want to leave you with a final, slightly provocative thought regarding the underlying implications of the architecture we have explored today.
What is your final takeaway?
We spent this entire deep dive marveling at how efficiently the GCN merges an individual node's personal features, like the text of an abstract, with the structural geometry of the graph to predict a hidden label. But consider the extreme edge case Kipf and Welling tested with the NELL knowledge graph. They provided the model with only a single labeled example per class, a single data point. And the network, primarily leveraging the sheer interconnectivity of the graph structure, was able to map out and classify the rest of the universe. From a purely information theoretic perspective, this suggests something profound about the nature of network data. It implies that in a sufficiently dense, sufficiently complex graph, an individual node's personal hidden features, the data we think makes a node unique, are ultimately mathematically redundant.
You are suggesting that the topology itself encodes the entirety of the system's variance.
Exactly. If a continuous Weisfeiler-Lehman algorithm can cleanly separate a sociological structure using completely random garbage feature weights, it means the connections themselves are the ultimate ground truth. It suggests that in the massive graphs defining our modern world-like social media networks or financial transaction webs, attempting to hide or obscure an individual node's specific traits is a mathematically futile exercise. The geometry of your connections alone, perfectly and deterministically, inlines exactly what you are to the algorithm.
The structure is the signal. That is a sobering, fundamentally true consequence of graph representation learning at scale.
And with that thought, we wrap up our coverage of semi-supervised classification with Graph Convolutional Networks. As always, we have put a link to the original Kipf and Welling paper in the description below so you can check out the math, the normalization proofs, and the Karate Club visualizations for yourself. Thank you so much for joining us on this deep dive into the source material. We will see you next time on Talk Tensors.